Hi, Physics 2. Mr. Janowski here. This is part 4 of the chapters 15 and 16 slides. So, quickly, the do now questions. Moving clocks run slow. What is this effect called? This is time dilation, and there's your formula for that. Now, moving meter sticks get shorter. What is this effect called? This is called length contraction. And there'll be a video later on where the guy calls it Lorentz contraction. It's the exact same thing. Length contraction is Lorentz contraction. And finally, so Denise and Alice will measure time and length differently if Alice is flying off to Vega at a very high speed. So what about velocity? So we know that there's going to be time dilation going on and length contraction going on. Is anything funny going to happen with the velocity? And the answer is actually no. They'll agree about velocity. They'll disagree about which one. They will disagree about which one's moving, and so which direction the velocity is in. But the magnitude of v will be the same for both of them. So, experimental evidence for time dilation. So, yeah, all the stuff we've been talking about so far, it sounds very weird and far-fetched, but I just want to point out that, yeah, we have very good evidence for this stuff, too. We've measured it, and it comes out exactly right. So, one thing happened in 1971. A group of physicists synced up atomic clocks with the very official atomic clocks that are kept at the U.S. Naval Observatory. They took the clocks, they put them on different planes, they sent the planes around the world, one going east, one going west, and then they brought them back together, and they compared the clocks to those at the U.S. Naval Observatory. And it turns out that the clocks on both of the planes disagreed with those at the U.S. Naval Observatory. So that's weird. So the clocks that were moving did experience different time. However, the difference, the lack of being in sync, completely agreed with the predictions of time dilation according to the theories of special and general relativity. So, yeah, there's some proof there. And then we also talked about muons, and I don't want to go through all the detail here because if this gets too long, then it will become unwatchable. So, yeah, for the detail, just read the slides. But this is another famous piece of evidence for time dilation and also length contraction. So the muons come down, they hit cosmic rays come down, they hit particles in the upper atmosphere. It creates this weird particle called a muon, and the muons come racing down towards the Earth about 20,000 meters below. So they're created 20 kilometers high. They come racing down towards the surface of the Earth, 20,000 meters below. The thing is, muons have an extremely short average lifetime. They only live about 2.20 microseconds, which is 2.20 millionths of a second. So very, very short. So even if they were going the absolute fastest speed that is allowed, and nothing with matter can actually go this fast, of 3 times 10 to the 8th meters per second, because they only live so briefly, they should only go about 660 meters. And I realized that I said I wasn't going to explain this all in detail, and here I am explaining it all in detail. So the gist of it is, let me click through the things. The gist of it is, how do these particles that live for such a short time make it down to the surface? And the answer is, for the observers on the surface and the detectors on the surface, they're going to see the muon's clock be very time dilated because the muon is moving so very quickly. It's moving 99.94559% the speed of light. Because the muon is moving so quickly, the detector on the Earth is going to say that the muon is experiencing time dilation. So it's going to say that the muon's clock is running very slowly. So it's running so slowly that the muon does have time to get down here. And the flip of that is, meanwhile, for the muon is going to experience length contraction. So according to the muon, the muon has proper time regarding the length of time that a muon will live. So how does the muon get 20 kilometers from the upper atmosphere down? Well, according to the muon, it doesn't go nearly that far. Because it's moving so quickly, let me rephrase it. You need to be precise about this. According to the muon, the surface of the Earth is rushing up so quickly that there's a lot of length contraction going on in that direction. And therefore, what the observer on Earth says is 20,000 meters, according to the muon, is only 659.67 meters. So yeah, this is how time and length contraction go hand in hand. So yeah, to review the muon thing, so all motion is relative. So if the muons are raining down, so this handy little graphic will explain what's going on. According to an observer on the Earth, the muon is coming down at this tremendous speed, 99.94, etc., the speed of light. And from the Earth, they see observed time, so delta t, and it's this. It is a very dilated time. But the Earth will measure the distance correctly. The Earth has proper length in this case. So it knows that, according to the Earth, it knows that from the surface to up here is 20,000 meters. Meanwhile, it's very different for the muon. According to the muon is at rest, and it's the Earth that's rushing up towards it. So again, they agree on the magnitude of the velocity. They disagree on which one is doing the moving and therefore which direction it's in. But the magnitude of the velocity they agree on. The muon again is going to measure proper time. Delta t naught is 2.20 times 10 to the minus 6 seconds. That is the proper, average lifetime of a muon. And the muon says that the distance from the Earth to itself is greatly contracted to only 660 meters, basically. So we didn't actually watch this video, at least in period 10, days 1 through. We didn't watch this video, but it explains the whole muon thing and everything that's going on there, and how time dilation and length contraction, really go hand in hand. If one thing has time dilation, the other thing is going to have the length contraction. And then we talked a while about this weird thing called the relativity of simultaneity. So simultaneous means happening at the same time. So the relativity of simultaneity means that two events that happen at the same time in one frame of reference. So according to one group of observers in one frame of reference, they say these two things happen at the same time can actually occur at different times in another frame of reference, which is very weird. So all of this time dilation, length contraction, and relativity of simultaneity. So even the idea of things happening at the same time becomes relative. This should be messing with your sense of reality. It is very weird. Now, these things only really become noticeable and dramatic at speeds very close to the speed of light, but they're totally true, all of these effects. So I don't want to go through all of this in great detail, again, because I want to keep the, my videos relatively, short and watchable. So, yeah, that stuff. Einstein, this is Einstein and his second wife riding on a train. So I explained the whole thing. And again, I'm keeping it short. If you want this in more detail, go through the slides very slowly. And I will also link up this video where Dr. Mike Merriweather at the University of Nottingham, who has many more letters after his name than I do. I don't actually have any letters after my name other than Junior, but he's a PhD. He explains this relativity paradox. And I think this is just a very neat little video, and he explains it very well. This bizarre paradox that length contraction and the relativity of simultaneity bring up. So that's it for these slides. Again, I'll put the links to these videos in the description to this video. So hopefully you found this helpful.